Good evening, everybody. We are about 7 minutes out from the release of the Day 5 puzzle for Advent of Code. Getting pretty excited here. Just getting ready. Thank you for everyone who's joining the stream. If you have any questions or just want to say hi, feel free to say so in the chat. Um, since last night, we worked. Sorry, one sec. Hey, go ahead. Making it a little bit harder for me to. Sorry, my partner is also in chat. I was just slightly distracted there, but we will be fine. It's no problem. So anyway, um, since last night, I thought a little bit more about Day 4's puzzles, and I actually got a really good idea for it from Elizabeth Hendrickson on Twitter, who I used to work with back at Pivotal. But she is solving the puzzles in Ruby and used regular expressions to validate all those different passport fields instead of writing custom validators like we did. And of course, when I heard about it, I thought, oh yeah, that would be a much more natural way to write string validators. Um, but sorry, just one second. So talking about regular expressions again. So the reason kind of why I didn't think to do this is because choice of language really matters a lot for how you approach these problems, and C++ doesn't really have built-in regular expression support. Now there are of course libraries that can give you that. RE2 is an example of one that I use pretty frequently in my work, but yeah, I mean, it just didn't occur to me. But I think that if you're in a language where it's like a scripting language that's more naturally suited to text processing and has built-in regular expressions like Ruby or like Python or Perl or anything like that, it's more obvious. So I kind of started tinkering around with that a little bit. I imported the RE2 repository so we can use those libraries in C++ if we find that that's more useful in the future. Um, I started tinkering around with just, like using, making a validator class that, uses an RE2 pattern to match strings. Didn't actually finish this up. I might, tinker with that more and, go back and revise my Day 4 solution. But I think, that just kind of illustrates that, there are, for a lot of these problems, you get to a place where there are a lot of different approaches, and sometimes the language that you choose to write in can really influence your thinking as to what approach that you take. I know that it certainly did for me because, writing things in C++, I'm just like, well, I'll just look at character by character, but really, regular expressions are a convenient tool that some languages it's easier to use them in than others. So we have about 3 minutes to go before tonight's puzzle unlocks. I've already set up our little skeleton directory here. We have just, our very bare bones outline of a main function for a C++ program. And we have the build file here to build it. And, I've just confirmed, we can run it here. It does nothing as we expect at this point. And this is the canvas on which we will paint our solution for Day 5's puzzles. So you have about 2.5 minutes to go. I can talk a little bit more about how I started this revision to the day 4 solution in the meantime in the couple of minutes that we have. So basically, you can make these RE2 pattern objects. And what I was thinking is we would have one of these field validators for each of the passport fields from the day before puzzle. And we have, optionally, if there's an integer that we need to extract and actually check its value, we can specify the minimum and the maximum for that integer. And then, so we fill in the RE2 pattern object, we check that it compiled okay. And then down here, we actually parse, and if we're expecting to see an integer in the pattern, we actually parse that out with this form of full match, and if it doesn't match the pattern at all, we return false. And if it does match, we check against the min and max if there are any here. And if there are no integers that we expect to parse out, we just make sure that it matches the pattern. And so you can start to see some of the patterns that I was writing here. Like, for years, these are all pretty similar. We expect 4 digits in a row. We have some mins and maxes. I started writing one for height, and, I realized, I was going to put an alternation group in here for, like, centimeters and inches. But then I realized that the conditions for the minimum and maximum value were different for centimeters and inches. So we would have to either make the field validator class a little more complicated to handle that, or another thing that we could do is just make a field validator interface and have different subclasses that that can handle things differently, and just make the height version a special case. All right, so we are just about 15 seconds away from the unlock of the puzzle here. It's getting exciting, folks. Wonder what this picture is going to be. We're going on a vacation of some kind, so maybe this is like ocean waves, and there'll be a beach down here eventually as the picture fills out. All right. There's always a little... okay, there we go. Binary boarding. You row your plane only to discover a new problem. You dropped your boarding pass. You aren't sure which seat is yours. All flight attendants are busy. A quick program using your phone's camera to scan all of the nearby boarding passes. Perhaps you can find yours through process of elimination. This airline uses binary space partitioning. Okay, interesting. Specified like FB, FBB, FF, RLR, where F means front, B means back, L means left, R means right. Okay, so first 7 characters will be front or back. So we use those to specify exactly one of the 128 rows on the plane. Okay. The last 3 characters will be either L or R. These specify exactly one of the 8 columns on the plane, numbered 0 through 7. Same process proceeds again, only this time with only 3 halves. Okay. Okay. Every seat also has a unique seat ID. Multiply the row by 8, then add the column. Okay. Easy enough. Okay. So this is going to be pretty easy. We just, calculate the seat IDs, and these. I mean, we're basically just parsing a binary number with some unusual format, but yeah. So let's just look at. We will go ahead and look at our puzzle input there. Okay, so these are all essentially 11-bit numbers. So I basically think, we're just... So, first thing we want to make sure is that the side, we'll just, as a basic safety check, make sure that we have exactly 10 characters. And then yeah, if we're doing a bunch of bit shifting, I just feel a little more comfortable making that unsigned. Call me superstitious, I guess. We're going to need I/O too to actually read the lines. So we can just switch. Well, so we start with 0, and basically each time we move to another character, we are shifting up the what number the previous characters represented. So we will left shift by what? Okay, that's maybe a little too. Sorry, that would be val. Okay. So basically, we do front or back, and for one seat, and that is a binary position of the space, but each additional space behind it is actually a smaller position. So we shift everything that came before it to the left. So then we will just do a switch on the character. So case F means 0, because it means the lower half. So we'll represent. So that's represented as 0. We'll OR in. We don't really have to OR in anything, but just for the sake of clarity, we'll OR in 1 there. Then back means that we OR in a 1 because at the lowest bit position, the one that we're currently parsing. And left and right mean something similar, essentially. So L means lower half, R means upper half. So we could validate that these front and back numbers are exactly the way that we have exactly 7 of front and back and 3 of left and right, but I don't think that this is really an input validation problem that we're trying to solve here. So we'll just let it be. And actually, now that I'm looking at this, we can use intentional fall through here and simplify this. So, because for front and left, we're doing essentially the same thing, and for back and right, we're doing the same thing. And then the default case here, if it's not any of these characters, we're in an unexpected situation, so we'll just check fail. And then we return val. So first thing I'm going to do before actually just finding the max is I'm going to just print out all of the parsed seed IDs so that we can do a little check here. So we'll make sure argc equals 2. Our two arguments are the program name itself and the file name that we want to read. We'll do our read lines from file routine. Check that we read those okay. Sorry, check OK. Then for each line that we read, let's just spit out the parsed seat number. And include IO stream. Go ahead and get the dependencies that we are going to need to put in here so that we can actually build with the libraries that we included. The only thing we need from Absol so far is strings, and we've got our check and our IO. So I'm going to use a few of the examples from boarding passes here and just make a little test file out of the stuff that they gave us on the website. So that one's supposed to be 567. This one's supposed to be 119. And this one is supposed to be 820. So let's go ahead and run our program, compile and run our program and test it. We have 567, 119, and 820. So that all looks okay. Yeah, we're just basically parsing a binary number written in a weird alphabet. So let's do it on the actual puzzle input. Well, okay, that's not actually what we wanted. We wanted to find the maximum value of the puzzle input. So we'll start with max seed equals 0, and then we'll just take the max of max seat and whatever seat that we parse from the line in that loop. And then we will go ahead and spit out the maximum value. Okay, that gives us 980. Let's go ahead and put that in the website and see if we got it right. All right, part 2. Ding, the fasten seatbelt signs have turned on. Time to find your seat. It's a completely full flight, so your seat should be the only missing boarding pass in your list. However, there's a catch. So the seats in the very front and back of the plane don't exist on this aircraft, so they'll be missing from your list as well. Your seat wasn't at the front of the bus, though, so the seats with IDs +1 and -1 from yours should be on the list. Okay. So basically, we just need to find the missing number in our list. Honestly, this is not. I imagine that we could do something fun with like bit twiddling and stuff, but the simplest thing I can think to do is just sort all the seats and look for the gap. So let's go ahead and do that. So I'm going to go ahead and copy our part 1 because we're source file because we're going to use that as the basis to start working on part 2. So we'll do puzzles day 05, part 1.cc. We'll copy that to part 2.cc. Okay. Refresh our view here. Get into part 2. So we'll use our same seat parsing routine. We will just make a vector of all the seat numbers. And, you know, we can reserve... This is completely unnecessary to have a correct solution. It's just like a tiny performance optimization so that the vector isn't resizing itself and reserving more memory, because we know exactly how many entries it's going to have. It's equal to the number of lines. So we'll go through here. We will put the parsed seat inside the vector. We will then use a convenient sort function from the standard library. So we'll just sort the full range of seats from begin to end. And then we will look for look for a gap. So we can do this pretty easily with iterators, basically. So what I'm going to say is for auto iter equals seats.begin, and it's going to be seats.begin plus 1, because we're always going to be looking at we're always going to be comparing to the previous seat, and we're not in the first or the last seat, we know. So if the value of this iterator does not equal the value of the previous position, plus 1, because we're expecting it to go up 1 by 1 by 1 until we find the gap, this is where we find our actual seat, because... And then the actual gap will be the actual number of our seat will be the number between the two and the gap. So it should be the value of the iterator minus 1, because the iterator is pointing to the second of the two seats that we're comparing. So we just want the one in the gap. So if we get there, we found it. We can return 0. If we get to this point, well, then something's gone wrong. We didn't actually find what we wanted in the gap. So everything dependency-wise should be exactly the same. And let's run our part 2 here and see where it says. Okay, it's going. It says. Oh, I didn't change the actual source reference. That's why it says 980. 607. Let's see if we got it right. Huzzah! Yeah, that's another one we got right. Let's see. Okay, I think this is probably our best performance so far. Yeah, it is. We're under 2,000 on both parts. You know, probably could have done this a little bit faster, but again, you know, I'm talking through it. I'm trying to, you know, explain what I'm doing here. So, yeah, reflecting on today's puzzle, this one, honestly, I think it's a pretty simple one. I actually think it's considerably simpler than yesterday's. But, you know, to each their own, because just, you know, like doing all that text munging yesterday took some more time. But essentially all we're doing, like what this boils down to is the you know, the F, B, and L and R way of writing out seat numbers is really just a way of writing a binary number with a weird alphabet. And the F's and L's are zeros, the B's and R's are ones. So, you know, we can just go character by character and from left to right and keep left shifting. Or I suppose we could have parsed it backwards and, you know, done it another way, but it doesn't really matter. I mean, it's just, we're reading a binary number in, and then for the part 2 solution, we could just sort and look for a gap. And again, I think that there is maybe, I have an inkling there might be something particularly fancy that you could do with bit twiddling, because this solution is still essentially n log n. I mean, the most expensive thing in this solution is just to sort all of the numbers, because parsing all of them is linear. We make one pass through, and looking for the gap is also linear. We make one pass through all the sorted numbers. It's just sorting them all into order is n log n. I guess one other. I mean, yeah. I don't know. I'll have to ponder this a little more if I think that there's something better. But honestly, when we only have up to, in our case, a maximum of 980 seats, that's not a lot of items to sort. You can do that pretty quickly. So yeah, that's it for today's solution. It's kind of a simple one, but a satisfying one once you realize, hey, these are all just binary numbers. And I think that the puzzle description really guided us to that too, when it wanted us to convert everything into a number, and it's like, oh yeah, that gives away the game a little bit. But yeah, that is our solution for today. So I'm about to end the stream. Like I said, I might tinker around a little bit more with my part 2 solution for day 4 to make it use regular expressions. These day 5 solutions will go up in the GitHub repo very soon. That is github.com/Craig-Chasseur/AOC2020. I will put that on the screen right now. You can see here's where the GitHub repo is. This video, as with all of these Advent of Code videos, will also go up on my YouTube channel at youtube.com/spoonboy42 later this evening. And yeah, thank you all for joining the stream, and I look forward to seeing you tomorrow for day 6. Have a good night, everybody.